So the next topic is Huffman coding. So Huffman coding is a technique. This is a compression technique used to reduce the size of a message. So suppose if that message given is BCC ABB DD AE CC BB AE DD CC. So and if you want to store a message in a file, or if you want to send that message over any communication channel, so instead of sending that full message, we should need to reduce the size by compressing that message. That means encoding. So suppose if you don't use any encoding technique, so that we are going to store that message as it is. So any character can be stored in a computer using a ASCII code. So ASCII code. So the size of the ASCII code is 8-bit. So for example, for A, the ASCII code is 95. That 95 will be converted into a 8-bit binary data. For example, this will be 1011000001. So this 8-bit is stored in that computer memory. So for each character, so to store that character as ASCII code in a computer, it needs 8 bits. So suppose if we want to store that message, the length of that message is 20. So to store that entire message, each character we needs 8 bits. So in total, so 20 into 8, so we need 160 bits. So while decoding 8, so we need to read 8-bit, so in a bitwise manner, 8-bit each time, and then that binary will be converted. The 8-bit binary value will be converted into a integer value. Then that integer value will be mapped with the corresponding. So integer value, that is integer value is actually ASCII value, and that ASCII value is mapped with the corresponding character. So we can able to easily decode the original message. So how the size of this message can be stored, so can be reduced by using any encoding method. So the simplest, there are two different types of encoding methods. So one is fixed size encode. So fixed size encoding. So and then variable size encoding. So the fixed size encoding, so we are going to so find a code for each character in the message, and the code is a size of that code is equal for all the characters. So irrespective of how many times that character appears in the message, so the same length code, while encoding, the same length code is assigned for each character. For suppose a character is appeared 100 times in that message, and one more character that appears only one time in the message. So for both the characters that appears 100 times and 1 times, we are going to assign the code with same size, that is fixed size encoding. And variable size encoding means we are going to effectively assign a code for each character according to its frequency, how many times that character appears in the message. So in the variable size, the code assigned for each character in the message is not same. So the character which appears frequently, so that means more times in that message, will be assigned with a code a minimum size code, and the character which appears less frequently in the message. So the less time, the count of that appearance of that message character is less, means that characters will be assigned with comparatively longer code. So that is variable size. So the size of the code is not same. So first we will see about the fixed size encoding techniques. So for this example, so we first draw one table. So that first column it contains that character, and next column it is that frequency of the character in the message, and then code. So what code, fixed size code, what code we are going to assign. So from this message, the character A appears for 3 times, character B appears for 5, character C appears for 6 times, character D appears for 4 times, and character E appears for 2 times. So since here we are not going to assign code based on the frequency, so whether the character which appear for 6 times C, and the character which appears for only 2 times E, so both the characters we are going to assign the same code. So now we have 5 different characters, so we need to find 5 different code. So if we need to find a 5 different binary codes, then what is the length of that binary code? So suppose if the length of the binary code is 1, the length of the binary code is 1 means, so we can able to generate 2 codes only, that means 0 or 1. So if the length of the binary code is 2, so if the length of the binary code is 2 means we can able to form 2 codes. So 4 codes, 0 0 0 1 1 0 1 1. So since we need 5 different codes, so with the length of 2 we cannot be able to form a 5 different codes. So we need to use a binary code of length 3. So if you use a binary code of length 3, then we can able to form 8 characters. That means the 2 to the power of n. If it is 1 means 2 to the power 1, that is 2. If it is 2 means 2 to the power 2, this is 4. So in the same way, if it is 3 means we can able to form 8 different codes. That means 0 0 0, so 0 0 1, so 0 1 0, so on to 1 1 1. So 8 codes we can be able to show. So the length of that code should be 3. The minimum length of that code should be 3, and we can form 5 different codes. For example, for A we can use 0 0 0, for B we can use 0 0 1, so for C we can use 0 1 0, and for D we can use 0 1 1, for E we can use 1 1 0 0. So this is the code we can able to assign for each character. So suppose if that message is like this, A B B, means we can send 0 0 0 0 0 0 0 0 1 0 0 1, and then while decoding we read 3 bits per 3 bits. and then the 3 bits. So for decoding, along with this message, we also send this table also. So for sending this, so if you have table with you, then only we can able to decode. So we read what is the size of that code, and while decoding we read that bits, 3 bits, but 3 bits, so 3 bits per reading. So and then by referring this table, we can able to convert that 3 code into a corresponding character. So if it is 000 means we can convert into A. If it is 011 means we can convert into D. So now, what is the size of this encoded message? So just forget this example. So for our example, so there are 20 characters. So instead of using a ASCII code with 8 bits, 8-bit code, now for each character we are assigning a 3-bit code. So totally there are 20 bits. So 20 characters, and each character we assign a 3-bit code. So in total 60 bits. And along with this, we need to send this message or this table also. So this table contains 5 characters. Okay, and for each character we need to assign 3 bits code. So totally 5 into 3 bits of data we need to send. So in total 60 plus 15 equal to 75. So the total size of this message will be 75. So this is fixed size encoding. So suppose if we use variable size encoding, whether we can able to reduce the size of that encoded message further. So we will check with one example of that variable size encoding algorithm that is called Huffman coding. So for Huffman coding, so I will take the same table, the character and frequency. So character and its frequency. So for character A, B, C, D, E, and its corresponding frequencies are 3, 5, 6, 4, 2. So now for this Huffman coding, first that frequency should be sorted in a ascending order. So now the frequency list is 3, 5, 6, 4, 2. So and the corresponding characters are A, B, C, D, E. So the first step is we need to sort this frequency. So sorted frequency. So this is 2, 3, 4, 5, 6. So this 2 corresponding to E, this 3 corresponding to A, this 4 corresponding to D, and this 5 corresponding to B, and 6 corresponding to C. So and then in Huffman coding, the actual procedure is we are going to form one tree that is called Huffman tree. So for forming this tree, so in each time we need to select 2 minimum frequency from the sorted array. So for example, so here the minimum frequencies are E and A. So the value corresponding to E and A is 2 and 3. So wait. So first we need to select the two minimum frequencies E and A. So this is 2 and this is 3, and we need in the tree we need to form a one more node, and the frequency of that node should be the sum of these two nodes. So I am going to create a new node with the frequency of 5. So and then so now I have frequency 5, and in that array I have three frequencies 4, 5 and 6. So this 4 is character D, and 5 is character B, and 6 is character C. And between these unvisited frequency values, so we need to include the newly created node also. So between these unvisited frequencies values, we need to select two minimum. So I select these two, 5 and 4. So you can also select this 5 and 4 also. So that also in this way also we can able to form this tree. But the condition is we need to select two minimum frequencies from this particular tree. So now 5 and 4. So the new node, the frequency should be sum of these two frequencies. 5 plus 4, that is 9. So and then next, from these remaining unvisited frequencies, we need to select minimum two frequencies. This is 5 and 6. So I select this 5 and 6 and the newly created node with frequency 11. So and then finally there are only two unvisited nodes only. So I select this two, and then I create that new node, that is the root of this Huffman tree, and with frequency 20. So first the leaf nodes are the frequencies 2, 3, 4, 5, 6, and each time I select two minimum frequencies in the tree. So and then I create a new node. The new node is a parent of these two selected minimum frequency nodes. So and then the frequency of that newly created parent node is the sum of the frequency of its child node. So and then so I'm repeating the same step until I select all the frequencies in the tree. So now I form the tree. So now I need to assign a code for each characters. So E, A, D, B, C. So actually this is it may create a confusion for you. So this is the node 2, 3, and this is E and A. Okay, so start from the root. I'm visiting its left and right subtrees, and each edge in the right subtree I am assigning a code 0. Sorry, left subtree I am assigning a code 0, and each edge in the right subtree I am assigning 1. So for this root node, the left edge as in 0 and right edge as in 1, and then I come to this particular node. So its left edge I assign 0 and its right edge I am assigning 1, and for this node its left edge I am assigning 0 and its right edge I am assigning 1, and remaining for this node left edge I am assigning 0 and right edge I am assigning 1. So now for the character E, so for character E, I need to traverse from the root node to that particular leaf node corresponding to the character E. That means this node, this particular node 2. So for this path, the corresponding code is 0, 0, 0. So for E, this is, so I fill this particular table for this E, this code. So for E, this is 0, 0, 0. So and then for A, so for A, this is 0, 0, 1. So for A, this is the path 0, 0, 1. So and then for D, so for D, the path is, this is the path. So that means 0 and 1. So for A, 0, 0, I fill the table. For A, that is 0, 0, 1. And for D, it is 0, 1. So and then for B, so for B, this is the path. So that is 1, 0. So for B, this is 1, 0. And then finally for C, that is 1, 1. So for C, so for C, this is the path. So 1, 1. So for C, this is 1, 1. So now, so what is the total length of this encoding? So for A, the length of the code is, this is 3, and for B the length is 2, and for C the length is 2, and for D also the length is 2, and for E the length is 3. So totally A is appeared for 3 times. So in total for A, 3 into 3, so this is equal to, we need 9 bits. So B is appeared for 5 times. In the message, B appeared for 5 times. So each time the B, to store B, we need 2 bits. So in total it is 5 into 2 equal to 10. And for C appears for 6 times, and for each time we need 2 bits to store. So 6 into 2 equal to 12. And for D, so D, that also that appears for 4 times, and we need 2 bits to store that character D. So in total 4 into 2 equal to 8. And for E, so E appears for 2 times, so each time we need 3 bits to store that character E. So in total 2 into 3 equal to 6 times. So if you add all this, then so in total the total size of that message will be, so 20, 26, 36, 45. So 45 is the total size, and for decoding, as usual, we need to send this table also. So in the size of that table is 3 plus 2 plus 2 plus 2 plus 3, that means 5, 7, 9, 12. So for storing this table, we need 12 bits. So 5, 7, 9, 12. So in total, so for message we need 45 bits, and for the table we need 12 bits. So in total we need 57 bits. So this is the total size of the encoded message using Huffman code. So without any encoding method, so it requires 160 bits. For storing this particular message, we need 160 bits of memory. So if you go for a fixed size encoding, then it requires 75 bits of memory. Suppose if you use this Huffman code, a variable type encoding method, then it requires only 57 bits. So the size of that encoded message can be reduced. And now what is the time complexity? So as usual, first step we need to sort that frequency, and then we are running one for loop. So in that for loop we'll execute it for n times. If the character number of characters in that message is number of unique characters in that message is n. So each time, so for n times, I'll execute for that for loop. Each time I'm selecting a character with two characters with minimum frequencies. So and then inside that for loop, I'm just adding the two frequencies, and I insert that frequency in that tree. So each time that creating a new node and assigning a new frequency for that node, it takes single unit time complexity only. So first step sorting, and next for n times. So for n times, what we are doing means, so select two frequencies, then add two frequencies and create a new node, and insert that node in the tree. So this sorting, so we can use merge sort or quick sort with time complexity of n log n, and this entire this time complexity for each step, entire step is a single time unit only, but this is executed for n times. So in total the time complexity of this entire code is n. So this is n plus n log n. So it may be O of n log n. So the same Huffman code, it can also be implemented by using a Min-Heap. So instead of sorting, we can also use a Min-Heap. So for this Min-Heap, first step, I just count the characters. So count the number of characters, that means C. So and then construct Min-Heap. So I'm constructing a Min-Heap. So Min-Heap, that is we can take it as H. So and then while H does not equal to null. That means there is until the h is not empty. Not we cannot say is that yeah, that's not equal to null until h is not empty. So each time I select a minimum from that min heap. So first x min select min. So select min from h. So and each time and each iterations we need to select two minimum values. But in a min heap, if you select the min heap minimum value, then that heap property will be destroyed. So again, I need to heapify that h. So once I heapify the h, then I select minimum. Now it will select the next two minimum in the list. So and then create a new node. Then eject of so eject dot frequency. The new node's frequency is assigned with x plus y. So and finally, so actually in this entire step, I am constructing that heap tree. Once the heap tree is constructed for assigning that Huffman code, we need the root of that heap tree, Huffman tree. So not a heap tree. So in this entire step, I am constructing this Huffman tree. Once the Huffman tree, so each time and I construct a heap node from the with the remaining values, and then I select two minimum values. So after selecting one minimum value, again I need to keepify that tree, and I select the next minimum. So this process will be repeated until the heap tree is empty. So once this process is completed, I construct that Huffman code. Once the Huffman code is constructed, I need to return the root. So only if I know the root, then only starting from the root node, I can visit the entire Huffman tree, and I can assign the uh, code for this Huffman tree. So now this is the min-heap approach. So suppose if you use min-heap approach, then what is the time complexity? So first for constructing this min-heap, so first step, this step is constructing the min-heap. So for constructing min-heap, it takes n time. So with suppose if we have a list of with a list of elements, n elements, so we can construct min-heap from that element from that list with the time complexity of n. So and then this is a while loop. This while loop will be executed for n times. So and then first in the while loop, first I do a select minimum from that heap. So the root node itself is the minimum in the min heap. So we need to first extract the root node only. So it takes only one time complexity, and heapify once the heap node is minimum is extracted, the root node is extracted, then again I need to heapify the remaining heap min heap. So the heapify process takes log n time. So again it means I am selecting the minimum. That means extra I am extracting the root node. So it takes one time unit, and creating a new node it also take one time unit, and then the frequency assignment for that new node also takes one time unit, and return state also takes one time unit. So these entire steps, all the steps will be executed for n times, because this is a while loop. The while loop until the h is not empty. So since the size of the h is n, so this will be executed for n times. So in total, so log n plus 1 into n. So this is equal to n log n plus n. So initially for constructing the min heap it takes n, So that is n plus n plus n log n. So this is n plus n plus n log n. So this is equal to 2n plus n log n. So it can be represented as O of n log n. So if you use sorting, so in this first approach I am using sorting. So first I sort, and then for each times I select two minimum frequencies and I add two minimum frequencies into the Huffman tree and create a new node. So and then inserting the new node. So this approach also takes n log n, and if we go for a min-heap, I first construct the min-heap and then until the min-heap is empty. So each time I select two minimum. So after selecting one minimum, I need to keep it, and then I select a second minimum and create a new node. So and then the frequency for the new node is assigned. Once that Huffman tree is fully constructed, I return the root of that Huffman tree. So this also takes of n log n time. Okay. So but which algorithm should be selected is based on the type of data that we are going to deal with. So this min-heap approach. So this min-heap approach that gives this O of n log n time is very much suitable for real-time data. So if you are dealing with the real-time data, so if you are compressing a data which is generated real-time, for example, if you are running a e-commerce business, so from your e-commerce portal you are receiving multiple data. So for example, in the morning you receive some 100 data. So and then you apply this Huffman code for compress that particular data. So and then after that evening also, so you receive after 1 hour you receive another 100 data. So for compressing, if you want to construct this Huffman code, we need to already we compressed one data, and then I receive a new node, and then we need to add that newly received message with the already existing message. So again we need to do the same Huffman code approach. So if you use a sorting algorithm, so then morning you receive 100 data, we will sort it. So and then you do that process, and after 1 hour if you receive 200 data means, so this data should be ordered with the already existing data, and then again we need to do the sorting. So each time when you perform this sorting, it takes n log n times. So suppose if you use a min-heap, so if we receive a morning, if you have some 100 data, and then you construct a min-heap, and then you extract minimum values from that min-heap, and then you construct the Huffman code. In the afternoon, if you receive 100 data means, so already we have one min-heap. So by just adding these 100 nodes one by one to that min-heap, and we can able to extract that minimum values from the min-heap. That means we don't need to construct that heap again and again. That n time for constructing a heap, we just eliminate it. Okay, so already we have that min-heap. So and then each here I just add the new data to the existing min-heap, and then I heapify that particular min-heap, and then I extract it. So that only one time it takes n log n time. So the first time when you sort that data, it takes n log n time, and whenever a new data is arrived, we don't need to sort it again. We just add the new data to the existing min-heap, and then I heapify it. So it just take only log n time. So for real-time data, instead of going for sorting, a min-heap based approach is best. So that is the difference between that sorting based approach and then min-heap based approach. In short, a min-heap based approach is efficient for the real-time data. Thank you.